Okay, so let's look at number 3. Number 3 is AC circuit problem. We have this AC source or alternating current source. In the previous chapters, we dealt with direct current using a battery or some direct current source, but here in this case this is the alternating current source. Okay, meaning in this case the EMF and current are changing with time. Okay, so it's not constant, it's changing sinusoidally with time. So this kind of curve is called sinusoidal curve, and we are asked to find the peak voltage across each of the resistors as well as the instantaneous voltages. So we know the EMF is given by E peak cosine 2 pi, oh sorry, not 2 pi, omega t plus phi. So that's the instantaneous EMF, meaning the value of EMF at any particular instant of time. So if you want to find the EMF at this particular time, you just plug this number in this equation and that will give you EMF. Okay, likewise if you want to find EMF at 20 millisecond time, you plug this time in this equation and that will give you the EMF. Okay, so let's first find the peak voltage. So this is the supply voltage or supply EMF, or you can say input EMF. Now we can compare this generic equation with the given equation. So this is E. So E naught is 100 volts. So compare term by term. E naught is 100 volts. Okay, that means our peak input voltage, okay, is 100 volts. This is the peak. Okay, peak is the maximum value. And phi, we don't have phi here. Okay, so that means it's 0. This phi is 0. Phi is 0 means it starts from the maximum value, like that. Okay, by the way, I drew the sine curve here. This is E naught sine omega t. Okay, because it's the cosine in the given expression, that means the curve should be like this one. So it would be E naught cosine omega t. So depending on where your wave starts, you can have sine or cosine. If it starts from 0 value, you have sine here. If it starts from the maximum value of the curve, then you have cosine here. Okay, so again comparing the variables term by term, this phi would be 0 because there is no phi given here, and then we have this omega t here. Omega t is that times t, so that means this thing is omega. Okay, this thing is omega. So our omega angular frequency is 2 pi times 60 hertz. Okay. Now we want to find the peak voltage across the resistors. Okay, so that means we will only deal with this peak voltage because that's what the question is asking in the first part. So let's reduce this circuit to a single resistor circuit, and we know that when the resistors are in series, you can just add the resistance, the individual resistance, to get this the equivalent resistor. So the equivalent resistor will have the resistance of 20 ohms, adding 5 and 15, and we are supplying a peak voltage of 100 volts. Okay, and again I'm using only the peak voltage because that's what the question is asking. If it asks the instantaneous voltage, then I need to use this thing. So that means this 100 volt will also appear on across this resistor, because this resistor is parallel to this source. That means whatever voltage you supply here would appear across this resistor. So this one has 100 volt potential difference, and we can find the current going through this resistor by using Ohm's law. So I is delta V over R. So delta V is 100 ohms, or 100 volts, and R is 20 ohms. So that gives us the current of 5 amperes. So there is 5 amperes current flowing in this circuit. Okay. Now, unlike in direct current, there is no single direction in the circuit. Like when we talked about direct current, we have a battery, and we know this longer side has positive and shorter side has negative. So the current flows from positive towards the negative. So that's the direction of current. But in case of alternating current, what happens is at one instance this is positive and this is negative, and in the next instance the polarity changes. Okay, this becomes negative and this becomes positive. So this happens continuously with time. So the polarity changes continuously. That's why it's called alternating current. The polarity alternates between positive and negative. So it becomes negative positive, and then in the next instance it's positive negative, and then again negative positive, positive negative. So it goes on forever, as long as you supply the source. Okay. So we have 5 amperes of current, and we know that these two are in series, and when you combine these two to form this one, whatever current you get on this one would also appear on the individual ones. So that means if we have 5 amperes here, then that means there would be 5 ampere current flowing through this one and 5 ampere flowing through this one. So each will have 5 ampere current. Okay, and this current is also called peak current or maximum current, because this is the current that we got from peak voltage. So this is also the peak current. We can just write I naught there. So now we want to find the peak voltage, and we know again from the Ohm's law. Ohm's law is delta V is equal to IR. So to find delta V here, or peak voltage, we just multiply I and R. So I is 5 amperes and R is 5 ohms. So multiplying those two, we get 25 volts. Okay, that's the peak voltage across this resistor. And same thing here. So delta V would be 15 times 5 amperes. That would be 75 volts. That's the peak voltage. Okay, V naught across this one, and this is the V naught across this resistor. And we can see here that the supply peak voltage is 100, and each of them is getting part of that. So this one gets 25 and this one gets 75. When you add them, that is the 100 volts. Okay, so this 100 volt that you supply here is divided between these two, and the one that has the higher resistance gets the higher voltage. That's what we see here. Okay, so that's part 1. Part 2 is asking for the instantaneous voltage, and we know instantaneous voltage E is given by this expression E naught cosine omega t plus phi. So for 5 ohm resistor, E would be E naught. So E naught here. Okay, so this is for the expression for the supply or source. When we talk about source, we use the term EMF. Now when we deal with the resistors, so instead of using the term EMF, we use the term voltage or potential difference. Okay, so instead of writing E, I will write V here. Okay, you can also write delta V. it's the same kind of expression. You have V is equal to V naught cosine omega t plus phi. You just need to replace E by V when you deal with the resistors or capacitors or any other component. EMF is used only when we are dealing with the source. So for 5 ohm resistor, the peak voltage or instantaneous voltage, so this is the instantaneous voltage, is given by peak voltage times cosine omega. Omega is that, okay, so 2 pi times 60 plus phi is 0, okay, and if you do the calculation you will get the answer. So this is in volts. Likewise, for 25 ohm resistor, the instantaneous voltage is given by V naught, same formula, cosine omega t plus omega plus phi. Okay, so V naught is 75 volts. That's the peak voltage across this resistor, and cosine omega is again it's same, 2 pi 60. Okay, so the frequency doesn't change when you have the resistors. Whatever frequency you have here, angular frequency, the same angular frequency will also be on each of the resistors. Okay, so we have the same angular frequency. Plus phi is 0, and you can do the calculation. So plug in the numbers in your calculator and that will give you the instantaneous voltage. Okay, so now let's look at number 4. You have 100 watt light bulb that is plugged into a 120 volt 60 hertz outlet. So this 60 hertz means is the frequency at which the alternating current is oscillating, okay, doing up and down, or in other words you can say in the 60 hertz outlet the current is changing its polarity 60 times per second. So plus becomes minus, minus becomes plus. That happens 60 times per second. Or you can also say it creates 60 waves like this one, 60 waves in 1 second time. Okay, so that's the frequency. So usually in our household the frequency of alternating current is 60 hertz, okay, and the voltage that we get is 120 volts. So we want to find the resistance of the bulb's filament, so resistance, and we also want to find the peak current to the bulb. Okay, so I want to find I naught. So this will be similar to the one we did in the DC circuit. In the DC circuit we define power is I times V, or I times delta V. So this 100 watt is the power, okay, and I is the current, and the current that we use in our household appliances is expressed in terms of RMS. Okay, so this current is RMS current. Like in the previous lecture we talked about this root mean square. It's kind of an average current. Okay, and root mean square current IRMS is related to this peak current, this maximum current, by this relationship. So IRMS is I peak over square root of 2. So current is IRMS and delta V is 120 volts. So we can find delta R, we can find IRMS by doing this math. So divide both sides by 120 volts. You cancel that. So then IRMS is 100 over 120. Okay, you can do the math. That will give you IRMS, which is in amperes. This should be in amperes. Now we want to find the peak current. Okay. Oh, by the way, we also need to find R. Let's first find R. Okay, and then we can find the peak current. So we know the Ohm's law. Again, use the Ohm's law. V is equal to I times R. So V is 120 volts. I is 100 over 120 amperes. Okay, that's that I, and that times R, and then you can do the math here to get R. Okay, so 0 and 0 cancel. You can cancel this 0 and this 0, and then 12, multiply both sides by 12 to get rid of the 12 here. So that means 12 times 12 is equal to R. So that means R is 144 ohms. Okay. I hope my math is correct. So 12, 120, 100 over 120. Okay, seems like that's right. Now let's find the peak current. So you can use this. We can use this formula to find peak current. We already know IRMS. Okay, this is known. That means I peak would be, to get rid of this square root of 2, you can multiply both sides by square root of 2. Okay, cancel square root of 2 and square root of 2. So I peak would be square root of 2 IRMS. Okay, so square root of 2 times IRMS is 100 over 120. Okay, so do the math. That will give you I peak. Okay, so now let's look at number 5. So this is a transformer problem. So we know a transformer has this common core. Okay, and coils are wrapped around the left side and right side. So this side we can call that primary coil, and this side we can call secondary coil. Okay, we can represent the number of turns in this coil by NP or N1, and the number of turns in this coil can be represented by NS, secondary numbers, or you can say N2, and the EMF or voltage across this could be represented by EP, E primary, and the voltage across this could be represented by ES or secondary EMF, and then the current in this coil we can write that as IP, and current in the output is IS. Okay, so this is, we can say this is output side, this is input side. Okay, and the function of the transformer, why we want to use transformer, like we talked about this in last lecture. So the transformer is used to either step up the voltage or to step down the voltage. Step up means increasing the voltage, or step down means decreasing the voltage. Okay, so let's see here. A book light has 1.4 watt 4.8 volt bulb that is powered by a transformer connected to 120 volt electric outlet. Okay, so we are connecting this primary side to 120 volt power outlet, and we are getting 4.8 volts on this side. Okay, so this is the secondary voltage and that's the primary voltage, and we are using that volts to light 1.4 watt bulb. Okay, so that's the power. Whenever you see the term watt, that's the power. Okay, power output is 1.5 watt. So we have E primary is 120 volts, E secondary is 4.8 volts. The secondary coil has 20 turns, and we want to find how many turns the primary coil has. So we want to find NP, and we also want to find the current in the primary coil. So IP is what? So we know this formula from our discussion last time. Vp over Vs is equal to Np over Ns is equal to Is over Ip. Okay, or you can also write E for that, same thing, EMF. So let's use this formula first to find the EMF, or to find the N primary. So part A, let's use EP over ES equal to NP over NS. So we want to find NP. NP would be EP ES times NS. Okay, just rearranging the terms, we get this. Plug in the numbers. EP is 120 volts, ES is 4.8 volts, and NS is 20 turns. So do the math, that will give you NP. Okay, and then to find the current, we don't have IP or IS. Okay, so to find IP we need IS, okay, because we need to use either this formula or this equal to that. So to do that we need IP or IS. Okay, but we don't have both IP and IS. That means we first need to find one of them, but we can find them by using this power outlet. So we know that power is I times V or I times E. So power is 1.4. Okay, and this power is the power on the output side, so it's on this output side. So power output is 1.4 watt, and I output or I on the output side is this IS, and E on output side is 4.8 times 4.8. Okay, so that means IS would be 1.4 watt over 4.8 volts. Okay, and if you do the calculation you will get the IS. So let's see what number you get. So 1.4 divided by 4.8, that gives us 0.291 or 2.292 amperes. Okay, once we have that, now we can use this formula. So we can use NP over NS is equal to IS over IP. Okay, so that can be used to find IP. So NP is, we just found that from here. Okay, so let's see what that is. So 120 divided by 4.8 times 20, that's 500. So NP is 500 turns. So NP is 500 turns. NS is 20, and IS, we just found that, so that's 0.292 amperes, and IP. Okay, so in order to find IP, we can do the cross multiplication. Okay, do the cross multiplication. Take this IP to the left and this 20 to the right. So that gives us 500 times IP is equal to 0.292 amperes times 20. So we can separate this IP. For that, we can divide both sides by 500. So cancel that. So IP would be that. So we can do that calculation. So that's 0.292 times 20 divided by 500. So that's 0.0116 0117 with rounding. Okay, that's amperes. So we are getting 4.8 on the secondary side. That means this is a step down transformer, but this step down transformer increases the current. Okay, you see our primary current is that, a small number, and our secondary current is that 0.292, which is greater than that. Okay, so the current goes up and voltage goes down. In the step down transformer, the voltage goes down and current goes up, whereas in the step up transformer, the voltage goes up and the current goes down. Okay.